the core concept or the problem actually we are aiming at is, if I have to strip it down to one line, that would be delay destroys value. Hi, my name is Cass, and I work with Axelerant as a data engineer, and I have been working with Axelerant for about more than 2 years now. So today we are going to talk about a real-time pattern detection system that we built here at Axelerant. We built it in a way which is dynamic, and we'll talk about what the dynamic part of it is. But before we dive into this, I'll first cover a basic few things which are relevant to the whole pattern detection system so that we build a base and go along. So the first thing that we want to talk about is data streams. Basically, most of the data systems that we work with, those work on data that are staying in a data store, right? Data tables or files. But data streams is fundamentally different, where we deal with data that is continuous and going in an unbounded flow. An analogy would be a river where water is flowing versus a lake or pond where this water after flow goes and rests. So you either work on the data that is in the rest in your data store, like in pond or lake, or you work while it is flowing within that river. The idea in both the things is different. In your data store, where you work later on, where your data files live in the form of tables and all, the idea basically is what happened to data. Whereas while the data is flowing, the idea is what is happening to the things right now. So that's the difference between a real-time system and a traditional data systems that process data after it has happened, right? So that covers the idea of data streams. The next part is, how do we process those data streams? Well, there are multiple tools available, but the one we have used for our use case here is Apache Flink. It's an open source project. And how it works basically is, it reads data from systems like Kafka, which is a data stream. If you look at it from that perspective, it's a data stream. You have Kafka after it, and then a sink. You process your data, which is flowing through a stream, and then your Apache Flink works in the form of different operators, processes on this data, and emits what it finds out, whether it's a detection, whether it's the transformation of the data into the sync part of it. What are those operators? What is this Apache Flink? It is a combination of operators, computational units, which can do different things like aggregations, transformations, evaluations across some rules, some patterns. The overall system looks like this. You have your data stream, which can be Kafka, you have Apache Flink, and then your sync, which is again a data stream like Kafka again, or a data at rest like your data store. Now, the core concept or the problem actually we are aiming at is, if I have to strip it down to one line, that would be delay destroys value. So one critical problem across the industry is that there is no lack of data, but there is a lack of ability to respond to that data while it is happening, while it is unfolding. So we want to target that part. While the data is flowing, how do we take action on top of that data? And then how do we make it dynamic so that even when the business needs change, without deployment text, without a delay, or without a regression or friction in changing those rules, we are able to make it happen, make those changes very effectively and very fast. That's what the dynamic part in this real-time pattern detection system is. So to explain how big of a problem this is and what impacts it as, let's talk through a few examples to understand that. So one of that could be a financial fraud problem. Fraud usually is a ring of operations in burst, many transactions happening in a very short window. And if detection happens after a transaction settles, the money is already gone. Maybe the detection was accurate, but it was not timely to act upon. So it's as good as useless. One more example would be if, for example, your credit card is being misused. What happens usually is, you have some transactions happening from one, let's say one country, and suddenly another transaction in a very different country. So while this is happening, you have another transaction happening from another country. You don't allow that transaction by detecting that in real time, this difference in real time, rather than allowing the transaction and later checking, okay, there has been a one transaction happened separately in some other country. No. Another example would be retail and e-commerce, where customer while is traversing through the site, the offers and suggestions that you provide in that real time would make more impact than sending a delayed email later that you may like this, right? So here again, customer intent decays very fast, and you want to work on it. You want to suggest very fast. You want to suggest in real time. So in each case, the value of the pattern decays rapidly, sometimes to zero, the moment the window to act actually closes. Next, I would like to talk about the type of patterns with these problems that we found out of our research. So to generalize, we found three type of problems or three type of patterns that exist. One is what we call as threshold, a simple stateless detection. Basically, what in our river analogy, if the water is flowing and suddenly you see a pH value increased, that is nothing to do with a state, a context of it. You just see a difference in what is happening normally and you just flag it. So you set a threshold of pH value, say 0 point something, and if it increases above that, you have a threshold crossed and you detect it. It's the simplest form of detection. In our general cases, how this would look like is, if for example a user's transaction is above, let's say $1,000, so in that case you would flag it off as something not usual. So that becomes your threshold pattern. Second pattern would be what we call as velocity pattern, which is we don't look at just the current transaction, what is happening, what just happened. Rather, we look at a window of time to see how things are happening and compare it with the current event. In your river analogy, process not just current possession of water, but what the water that has already passed through you for, let's say, past 1 hour. If the value of pH has been going up and down, then accordingly you take a decision whether this is really something to flag off or not. And in a technological perspective or in real use case, it will be, for example, a user has made more than 10 purchases in last 1 minute. So in that case, you would want to flag it off again. It is not usual. The third type of pattern is something what we call as correlation pattern, where you don't just look at data in one stream, as in your data is flowing, you just look through a time window, or you just look through one event that has happened currently with a threshold. Rather, you compare this event with something that is in another stream or somewhere else. For example, you relate the data that is going through currently in your event stream to something else to correlate whether this is normal or not. One example of correlation would be, for example, this transaction that is going through looks suspicious, not just because of its value or how past transactions happening, but because the account to this transaction is being made to has been recently created. So there is a separate context around which tells if this is not normal. There is some additional context to it which adds meaning to this event, and then we flag it off accordingly. Another example would be astroturf detection, which is a network of low reputation accounts coordinates to artificially amplify a hashtag or a topic on social media or somewhere. So what we basically do is you detect a trending topic. The users of the trending topic, how do you detect if they are bots or some low reputation users? Is you have the events flowing in, all the posts that they are doing. You correlate the user with another data sitting somewhere, maybe in a stream, maybe some object storage or data storage, and you check against each user that's making that post how reputed this user is, or how often he makes posts, or how does he really look like, whether he's a bot or not, and accordingly flag off those posts that these are not real posts. That becomes another example of correlation. Okay, the next part that I want to talk about is the dynamic part of this whole pattern detection system, right? So most of the detection logic, most of the detection systems out there that are already built, how do they differ from this one is that those detection systems hard code the logic, business rules to detect those patterns within the job itself, within the infrastructure itself. For example, you want to detect those threshold rules. You have defined $500 as a threshold. Each transaction crossing $500, you would flag it off. But now, if the business changes and now you want to change it to 300, now what it requires is changing the logic in the job itself and then redeploying. Now, this does not really look like a problem. Problem actually occurs when we look at the type of jobs that we just described: threshold, velocity, and correlation. The threshold one, where It's as simple as just you read the data that's coming in, apply a threshold on top of it, and then flag it off whether it qualifies or not. But this actually is stateless, right? That's the reason it is simple. But if you look at something which is stateful, where your job is not looking at the current event, but it is also looking at a window, in that case, stopping a job, redeploying it, adding new rules to add new rules basically is a problem, because you may lose the in-flight window state. So there is a risk of adding a gap where you do not know what happened. Now, how do we address this is we treat the rules as data, and we let not just the data evolve, that is your events evolve, we let the rules evolve too. So in real time, you can go and update your rules. It is treated as data. Your Flink job sees those rules as data itself, ingests it, updates it, all its operators, and acts accordingly with no deployment text, with no change or no gap. It's implicit within the system that your rules are treated as data, and it updates its system. So a rule change is no longer a deployment. It's publishing a new message to say Kafka topic. The job picks it up and applies it immediately to the next event. No restart, no state loss. This is just rule as data principle. And this is what is the dynamic part of our real-time pattern detection system. Next, we want to talk about the architecture of the system. Basically, that would incorporate how the data flows and where it flows from where. So how we have designed the system is in the form of three streams. We assume the main events, your main data, the river actually flows through one stream. Let's call it events, or when we create a Kafka topic, we called it in our example as events.raw. So your raw events flow through that stream. Second, which is your most important part, is your rules. So we pass our rules through another Kafka topic or another stream. So rules.active. Why I use the term stream is because now we are treating our rules as data. So you have river one where your data flows, another river, or let's just say a pipe where your data flows through is your rule stream, where your rules that apply on this data flow through. So we call it rules.active, but you can call it anything. It's configurable. Then another or third one is the context stream, where the third pattern of ours, correlation pattern, fits in, as in where your context flows in. Now, this context can be a data store somewhere else, but to begin with, we started with this assumption that it is flowing through a stream again. So you have context dot raw, or just context named stream, where your context flows in. And this context could be the user profiles or the newly created users, all those stuff, which actually tells you some additional information about the events that is flowing through your event stream. Flink, the application that consumes from all three of those. Flink, the application that consumes from all three of those streams. It consumes the event raw and flows all the data through its operators to check the data against the rules. Now, your rules, when a new rule is coming into the stream, your Flink reads that rule, knows that it is a rule now, which it has to pass through all the operators. It uses its internal system called broadcast state. It passes this rule each and every one of the operator, and those operators store this rule in their own state, so the next event when that flows in, even immediately it acts upon that event based on the new rule it just ingested. And the concept that it uses is broadcast state. The architectural principle, the event stream and the rule stream evolve completely independently. So your events flow non-stop, and your rules can be updated any moment or whenever there is a business change, and those rule updates take effect immediately. No restart, no disruption. So for this, we leverage Flink's mechanism called broadcast state. So for every record from the broadcast stream, which we treat our rule stream as, is delivered to every parallel working operator, and it updates its internal rule in what it calls as state. So it keeps that newly updated rule in its state, and then whenever the new event flows in, even immediately, it acts on that event based on the rule it just stored. So no central coordination, no locking, no restart. This is what we call as hot reload, the actual dynamic part. So your rules dynamically update your whole system. Okay. Well, next, I would like to talk about a few technical bits which are important when it comes to real-time patterns. So one is processing time versus event time. Processing time is the time when the event reaches your system. For example, your IoT sensors are sending data continuously, but there is a lag in sending the data. it was not connected to network. But then when it lands into your event stream, that's the time we call processing time. And second is your event time, which is when the event actually happened at the source. Now, why the processing time versus event time matters is, if a velocity rule counts events in a time window of lasts 10 seconds and you're using processing time, a late arriving event, let's say happened 8 seconds ago, but arrived 3 seconds late, might land in a completely wrong window, right? You have a new window after those 10 seconds of window, your next window starts and your data just appeared. So this data actually belongs to the previous window, but you counted in a wrong window. So that's your processing time. But if you do it based on event time, in that case, it will be sorted and put into your right window of the data. So that's why it is important. And this is configurable in our system. There's a parameter called time mode where you set processing time or event time. Okay. Next is watermarks, which is a very well known and very important concept in case of data streams and real time processing of streams. A watermark is a way of handling late arriving events. It is basically a signal which is injected into the event stream saying, I am confident that no event after this timestamp, earlier than this timestamp, will arrive at this point now. So it is like a closing window that no event beyond this timestamp will come in now. So you add just a sort of buffer. For example, if we set a watermark of 5 seconds, it would mean for the Flink to wait 5 more seconds before it considers current window as closed. That means late arriving events, if they are up to 5 seconds late, they'll be considered in the same window. If they are more late than 5 seconds, then those events are dropped. Okay, next thing that I want to talk about is context resolution modes, which is not native to real-time pattern detection or data streams, but it is within our system. So the third rule that we talked about, which is the correlation pattern, is where we use a context stream where context regarding the data that is flowing through happens to be in this stream. Now, this context can be in various ways. For example, you're processing financial transaction rates. You're making transaction in one currency and then it is appearing, or the transaction is happening in a base currency, right? And your context of the transaction, how much is the conversion rate, lives in your context streams. What happens that this conversion rate can change continuously. So you may have more than one entries of, let's say, INR to USD in your context. Now, which one to take as the right one, which is what is the value right now of INR to USD? There are basically multiple types of those modes. One is last, where you treat the last entry as the most valid entry. So, in other words, what do we know about this entity right now? There may be more items or more entries of this record in the context window, but those are meaningless. For example, 1 hour ago, $1 may have been 90 rupees, but at this moment it is 91 rupees. So past entries do not make sense. So what is happening right now? What is the current context? So that is when you use last. Likewise, you have mean, where you want to calculate the mean across all the values that are present in the context window and compare the current event with that mean. So the question here would look like, how does such events usually look? Likewise, there is another which we call as mean standard. We use MEAN_STD, which is basically a z-score calculation. So it is like how many standard deviations from the normal this event looks like. Okay, last but not the least, let's talk about the business impact and practical applications of this whole system. One application of this system could look like you use the system to detect a pattern of use transactions that are happening for a particular user. And if there is an unusual transaction, like it has happened from a different IP address from a different country, or it does not look like the usual purchasing pattern of the user, then you flag it off, send them confirmation message, and then get confirmation, then allow it. Another is you detect from the institution's perspective if more than X transactions are happening in let's say T amount of time, then we are likely in an attack. We can detect early DDoS attacks or early financial attacks on an institution with this. more like a velocity pattern. Another would be trust and safety. AstroTurf, examples like AstroTurf can come in coordinated and authentic behavior. Basically, your velocity rule, for example, can say more than n posts for the same hashtag are happening in X seconds. So you go and look at it, and then you add a correlation on top of it that cross references those users that are making the post against the user profile, where we have, let's say, the time of the account being created or the user reputation. Let's say if a user reputation is less than say zero point 0.5, then you flag off all the posts by that user as inauthentic. Okay, so the underlying principle across all of these is that insights that arrive while the situation is still unfolding enables intervention, while insights that arrive after only allow explanations. That's all. Thank you.